polyprotic acids. They contain 2 or more ionizable protons. Those protons come off one at a time. Unlike the bases, they release all their hydroxides at the same time if they're going to do that. Here we've got sulfurous acid. It can remove 1 hydrogen ion. And then we've got hydrogen sulfite ion. The hydrogen sulfite ion also has an ionizable hydrogen, and it can release that and give us the sulfite ion. These are 2 separate reactions. They each have their own equilibrium constant. So we'll sometimes call this Ka1 and Ka2. The second Ka is always smaller than the first one, and it's actually much smaller. It couldn't be larger, could it? Because you couldn't release more than this one formed, right? So this one's going to be much smaller. And that makes sense when we think about it. The hydrogen ion here is leaving a neutral molecule. Here, the hydrogen ion with a positive charge is leaving a negative ion. And so there's a charge attraction there that makes it harder for it to leave. So here are some common polyprotic acids and their ionization constants. And so the columns here, the first one gives Ka1, Ka2, and then we've got a couple that have a third hydrogen that can be released. You don't need to memorize those Kas. Sulfuric acid is in our list of strong acids. It's only the first ionization that's strong. So you put sulfuric acid in water, it's going to completely ionize into hydrogen sulfate and hydrogen ions, but then the hydrogen sulfate will act as a weak acid. We can identify these polyprotic acids because when they're written correctly, they're going to have H2 or H3 at the beginning. Because like this one, citric acid, ascorbic acid, you may wonder, well, why don't we put all the H's together? We don't do that because the first H's are the ionizable hydrogens. Those are the ones that can come off when it acts as an acid. And the hydrogens back here, this H5, those are not going to come off ever. So the first Ka is much larger, and so it's going to form a lot more hydronium ion than the second or the third steps. And the formation of the hydronium ion in that first step actually inhibits the formation of hydronium ion from the second step, because hydronium ion is a product in the second ionization. So most of the time, we can treat polyprotic acids as if the first step were the only one. We can just look at the Ka1 and do our calculations from that. A very significant exception is a dilute solution of sulfuric acid. Dilute solution of sulfuric acid, you do have the complete ionization of the first proton, and you also have to consider the second one as a weak acid. Okay, so find the pH of a 0.050 molar carbonic acid solution. Nope, I didn't give myself the Kas. I'm going to go back and look it up. Carbonic acid. Jeez. My short-term memory is not what it used to be. 4.3 times 10 to the minus 7 is the first one, and 5.6 times 10 to the minus 11 is the second one for carbonic acid. Okay, now I can do the problem. So find the pH. Looking at this formula, we see H₂SO3, that's a diprotic acid. We're going to look at the first ionization. So, ice table. So H₂SO3 is going to be in equilibrium with H plus and HCO3 minus. Just take one of the hydrogens off. So the concentration given there, the 0.05, that's the initial concentration of the weak acid. And we will assume that the concentration of hydrogen ion is essentially 0 because it's so small. And the concentration of the hydrogen carbonate ion is 0. Then we use X to stand in for the change that's going to happen. So carbonic acid is going to change by negative X, and our products are going to change by plus X. Hopefully this is comfortable and familiar by now. So at equilibrium, we end up with the concentrations described as 0.05 minus X, X, and X. And we can put those into our equilibrium expression. We're going to use Ka1 because we're looking at the first ionization, 4.3 times 10 to the minus 7. And that's going to be equal to X times X, X squared, divided by 0.050 minus X. So I'm just going to stick that in my solver. I'm getting, 1.46 times 10 to the minus 4. If you do the X is small approximation, then you don't need a solver because you can just do it with simple algebra. I just stick this directly into my solver on my calculator. I mean, you can always try the X is small approximation, and I think in this case it would have worked. But in my opinion, that just involves a lot more thinking, and what does it save us? It doesn't actually save us anything because it takes longer to do that. The X is small approximation was really important before we had such awesome calculators. So that is the concentration of hydrogen ion, right? Let's look at the contribution from the second proton. So we would do that by looking at HCO3 minus and see how that acts as an acid. Now, for the initial concentration, it's not this 0.05. It's the concentrations that we found after the first ionization. So the concentration of HCO3 minus is equal to X, which is what we found here. And is the concentration of hydrogen ion approximately 0? No, it's X. 1.46 times 10 to the minus 4. What about the concentration of carbonate ion? That's 0. So is this equation going to shift towards to the right or to the left? It has to go to the right because there isn't any carbonate, so it can't go backwards. So this is plus X, this is plus X, and this is minus X. If you identify the direction wrong, you'll end up with a negative X that will work. You plug it in and it'll just take care of it. So then we get 1.46 times 10 to the minus 4. So at equilibrium, we have 1.46 times 10 to the minus 4 minus X. And our hydrogen ion is 1.46 times 10 to the minus 4 plus X, and carbonate is just X. Our Ka2 is 5.6 times 10 to the minus 11, which is significantly smaller. And we plug all this in here. So put this in my solver. 5.6 times 10 to the minus 11 is equal to the quantity 1.46 times 10 to the minus 4 plus X times X, and divided by the quantity 1.46 times 10 to the minus 4 minus X. Close parentheses, solve. Okay, my calculator, I don't know what yours is doing. Mine's giving me this 4.087 and a whole mess of nines. And you're like, it can't be 4, right? This is way too big. If you go way over to the edge, there's an e to the minus something. And it's not going to show it to me unless I scroll over there. It's e to the minus 16. So calculators can be a little dumb sometimes and not, I don't know why it displays it that way. Did anybody else get that result? 4 times 10 to the minus 16? Nobody?
I want to redo it.
Well, because I may have done it wrong. 5.6 times 10 to the minus 11 is equal to 1.46 times 10 to the minus 4 plus X times X divided by the quantity 1.46 times 10 to the minus 4. I did, my exponent down there is minus 4 minus X. Not sure how that happened, but that's not good. Then I accidentally pushed the delete button, and so then I had to do the whole thing over again. Okay. So yeah, so now I'm getting 5.599999. Let's just erase this. So we'll call that 5.6. And times 10 to the minus, and I've got to scroll over there to see what it is. The suspense is killing me. Yeah, it's minus 11. I just have to see for myself. So that's what our X is equal to for this second ionization. So when we're doing the pH, we would take this 1.46 times 10 to the minus 4 and add 5.6 times 10 to the minus 11. Is that going to do anything? No. The second ionization does not contribute significantly to the pH of the solution. So we did not need to do all of that, but I did it to show you that we don't need to do it. Yay. What the heck? Okay, so we still haven't answered the question. So we need the negative log of our original X and we get a pH of 3.84. So all of that, didn't need it. This down here is our hydrogen ion concentration. Any questions?
How would you know not to go to that second step?
That's a good question. How do you know not to go to the second step? Can you just always assume that? Almost all the time, the second step of a polyprotic acids ionization is not going to matter. And when we look at these Ka values, we've got 10 to the minus 7 and 10 to the minus 11. That's a difference of 10,000, a factor of 10,000. That's a lot smaller. The one exception is the sulfuric acid. You gotta pay attention to the second one. And look, here we got the sulfuric acid solution example. Yay, right? Okay. I need, oops, there it is. I need the Ka for that second one, 1.2 times 10 to the minus 2. So that's significantly larger, isn't it? 1.2 times 10 to the minus 2. That's our Ka2 for sulfuric acid. Okay, so we're going to make a nice table. Of course we are, because that's what we do. So H₂SO4 to H plus HSO4 minus. There's no Ka for this because this is strong. So this is not an equilibrium. It goes all the way. We could still set up a nice table. The initial concentration of sulfuric acid is 0.0075. The initial concentration of the products is approximately 0. Here we know that it all goes to the right. Our ending concentration of sulfuric acid is going to be 0. So our change is minus 0.0075 plus 0.0075 and plus 0.0075. Now, did we have to do that? No, we didn't have to do that, but you can. It doesn't hurt anything. It might help you think about it. So after the first step, which is strong, now we have concentrations for the hydrogen ion and the hydrogen sulfate ion. And then we're going to look at the ionization of the hydrogen sulfate ion. This is a weak acid, and so we've got H plus and sulfate ion. Our initial concentrations are going to come from the ionization of that first proton. So we've got hydrogen ion being 0.0075 and the hydrogen sulfate ion is 0.0075. And we'll say that the sulfate is 0. And we're going to look at the change. And this is going to be minus X. And plus X. And plus X. So at equilibrium, 0.0075 minus X. 0.0075 plus X. And X. Ka2 is 1.2 times 10 to the minus 2. And so we've got .0075 plus x times x divided by .0075 minus x. Solving. I'm getting .00385. So I'm supposed to find the pH. So for that I need the hydrogen ion concentration at equilibrium and the sulfate ion concentration. Well, the sulfate ion concentration is X. Right? So this is equal to the sulfate ion concentration. The hydrogen ion concentration, I have to use this term. Come on, pointer. Come on, pointer. Won't work now. There it is. This term, .005 plus x, .0075 plus .00385. .01135. And then pH, over here to the left, pH negative log of that hydrogen ion concentration. .95. Now, the significant figure Nazis would have a field day here. But as much as I love significant figures, really the purpose of them is so that we have a reasonable precision in our final result. As I was grading some of your experiments, a few of you rounded a little too much. You took a temperature in Kelvin that had 3 significant figures, or maybe even 4, and then when you inverted it, you dropped it down to 2 sig figs. So doing things like that can introduce rounding errors. So when in doubt, keep a couple extra digits. I wasn't really keeping track here, but I was thinking, well, I'm going to have to subtract from that, so I don't want to round it too much. I'll keep this extra one. And then when I rounded the pH, I was thinking about, well, what kind of precision did I have on my original numbers? Well, that had 2 significant figures, so I'll go with 2 sig figs in my pH. It's just, we want to get approximately right. Any questions? Yeah.
So we have the Ka1 because that dissociates completely?
Right. It's a strong acid, so there's no Ka1. Yep. Any other questions? Finding the concentration of the anions for a weak diprotic acid solution. Sometimes we might want to know what the anion concentrations are. Now, the contribution to the hydronium ion concentration from the subsequent ionizations may not be important, but we might want to know what the ion concentrations are. So if we want to know this one, we're just going to calculate And we'll find that the hydrogen ion concentration and this first ionization anion are going to have the same concentration. If we want to know what this one is, then we have to do the second step like we did on that first problem that I ended up crossing it out because that was not needed for the hydronium ion concentration in our final solution. But if we wanted to know what the fully dissociated anion was, then we would need to go there. So of course, we're going to go there. But look, this is find the carbonate concentration of the 0.05 molar carbonic acid solution in, for practice, 16.17. That's the one we did, where we did the extra stuff. So instead of doing this all over again, I'm just going back and well, I thought maybe I could erase the scribbled out part, but I can't. That's fine. Because I am a chemist and I am accustomed to writing in lab notebooks, and I did not obliterate this, right? I just drew a big X through it and we can still clearly see what it says. So, right? So this work that we did that seemed fruitless before, now in this later problem, they're wanting us to give the carbonate ion concentration. So the carbonate ion concentration comes out to be X in this second ice table. And so there is our X, which was not at all useful in finding the pH, but that is the carbonate ion concentration. It's very small, but it's not 0. Any questions? I'd like to say that I planned ahead and did that on purpose, but I didn't. That was just dumb luck. So this is going over the dissociation of a polyprotic acid. So here we have this guy, and it loses one hydrogen ion and forms an anion, and so we can calculate the hydronium ion concentration from this first one. Then we see the second ionization, and you can calculate that, and we see that that is insignificant in comparison to the contribution from the first step. We add those together, and the second one doesn't matter at all. So this is an interesting statement down here. The concentration for X2 minus, that fully dissociated ion, for a weak diprotic acid is equal to Ka2, provided that the X is small approximation is valid. So we came out down here and we got X is equal to 5.6 times 10 to the minus 11. That's what the Ka was. And we need a soundtrack of the Twilight Zone music.